Now we're going to look at preventing pressure sores in detail later on, but let's look at in passing now how shearing forces can be prevented. I think you can see that this patient is not going to slide down the bed for several reasons. He's going to resist that tendency to slide down the bed in this direction. That is resisted. The first thing it's resisted by is there's a bedboard with a pillow here that the patient can press his feet against. So he can use his leg muscles to keep his sacrum and his back pushed up that way to stop him sliding down. Also, he's got something under his knees here that will prevent his hips from sliding down the bed. Also, he's fairly well positioned. He's sitting up the way at quite a nice angle. Again, that will help him. That will help to prevent him sliding down the bed. So prevention of shearing forces there in a patient on bed rest. Now, I know some of you are getting perturbed at the moment because I've actually got an object under the patient's calf muscles. And in a previous video, I've advised against this because of the possibility of deep venous thrombosis formation. But the key thing actually is not that there's something under here, but that the pressure on the calves is equal if there is something under here. That there's not a particular point of pressure on the calf muscle. So very often these things are a matter of you judging which is the greater risk. But if there's a soft pillow with a small amount of pressure and equally distributed, then perhaps the risk of DVT is less than the risk posed by shearing forces causing pressure sores. But certainly don't have anything hard or lumpy or protruding into the calf muscle. So think of ways to support your patient in bed to prevent shearing forces. This is only a couple of my ideas here. Now, of course, I think you can see that shearing forces can equally well apply when a patient is sitting as they slip down the chair. And this is prevented in this caption in a couple of ways. One is that the patient, with his knees bent, can reach the floor and he can apply force with his feet to keep himself up and stop him slipping down. So you don't want chairs where your patient's feet can't reach the floor to support the legs and the bottom part of the body. As well as that, he's propped into the chair at a nice angle of 90 degrees, so he's less likely to slip down the chair. So consider shearing forces in patients that are in bed and also in patients that are sitting, because tissues can be damaged just as much by sitting as they can by being in bed. So when pressure is applied to an area, it goes white, as we saw with my fingers on the glass screen. And the reason it goes white is because the circulation is occluded by the pressure. Now, once the pressure is relieved, again as we saw on the glass screen, my fingers went red again. But if I kept that pressure on for longer, then the redness, well actually when my fingers went red again, they just went back to how they'd been. But if it had been kept on for longer, then you get what you call a reactive hyperemia. The area would go red. So in other words, reacting to the pressure, there would be a hyperemia. And a hyperemia, hyper means greater than, emia means blood. So there's an increased blood supply. So after the pressure has been relieved, the tissues are all very short of oxygen and need to get rid of a lot of waste products. So the body increases the blood supply to that area to compensate for the time that it's been under pressure. That's called a reactive hyperemia. So the reactive hyperemia, when the pressure is taken off, is the body compensating for the period of reduced blood supply by increasing the blood supply. But as well as that, as nurses, we can make use of this, because if a patient is getting red areas, if they're marking, then that means that the area has been under pressure because the reactive hyperemia has been necessary. So red areas mean that the area has suffered from too much pressure and that pressure needs to be relieved. And the key point, again as we've stressed before, at this stage, when there's only a redness, when there's a reactive hyperemia, the pressure effect is reversible if the pressure is relieved. Therefore, we can prevent a pressure sore occurring by regular observation of the surface of the patient's body to make sure that this redness due to pressure is not occurring. Or if it does occur, to take the pressure off it. We've made it clear that the pressure impairs or occludes capillary blood flow, producing ischemia. So ischemia is likely to develop, as we saw with the sphincter cuff, at a pressure of 25 millimetres of mercury or more. So 25 millimetres of mercury will occlude capillary filling. Therefore, given time, pressure sores will develop. And as we've also said before, there's a critical period of time. So the capillaries need to be closed for a particular period of time. And over this time, localised tissue necrosis will occur. Now, before we look at the effects of time, first of all, I want to look at the effects of pressure on various surfaces, just looking at pressure to begin with. Now, this graph shows pressure figures on a hard floor, made of lino, in fact, in this case. So on a hard lino floor. And what we have here is these figures are the amount of pressure. So this at the bottom here is the hip. So when you're lying on a lino floor on the patient's back, there's 112 millimetres of mercury transmitted through the hip. Clearly way more than is necessary to cause pressure sore formation. The heel, this is the heel here. Through the heel there's transmitted 55 millimetres of mercury pressure. Again, more than enough to cause pressure sore formation on the heel. This is the shoulder here. And at the shoulder there's 116 millimetres of mercury. And in the sacrum, if the patient's lying on a hard floor, a huge 238 millimetres of mercury. So pressure is transmitted through the pressure points of the body when the patient is lying on a hard linoleum floor. These figures were taken by measuring the amount of pressure between the patient's body and an operating table. Here we see at the hip the pressure was 66 millimetres of mercury. At the heel it was 71 millimetres of mercury. At the shoulder it was 82 millimetres of mercury. And again, highest by far, the sacrum, 232 millimetres of mercury of pressure when a patient was lying on an operating table. All well above the 25 millimetres of mercury necessary to start off pressure sore formation. Now, this group of readings were recorded between the patient's body and a sprung mattress with springs in it. And here we have the hip at 34 millimetres of mercury, the heel at 34, the shoulder at 36, but the sacrum still high at 72. So even though the pressures are much less, still in time pressure sores will develop with an immobile patient lying on a sprung mattress. Here we have the figures for a foam mattress. The hip, 32 millimetres of mercury. The heel, 36. The shoulder, 37. And the sacrum, 43. So less than hard surfaces, but nevertheless, pressure sores will develop in time. And these figures are probably very comparable to what you get on an ordinary foam type mattress in an English hospital. The only example that we've got here where the figures are actually below 25 millimetres of mercury are this bed which has been made up of feather pillows. In this case the pressure on the hip was 13 millimetres of mercury. On the heel it was 16 millimetres of mercury. On the shoulder it was 18 millimetres of mercury. And on the sacrum it was also 18 millimetres of mercury. But of course, given time, the feathers would have been compressed anyway, and the pressures would start to increase again. So what we're seeing is that the pressure exerted by all of these common surfaces that we nurse patients on are greater than 25 millimetres of mercury. So if the patients are not moved, the position of the patients is not changed to relieve the pressure, then pressure sores will develop. Now we said there was two factors in pressure sore development. One was the amount of pressure, the other was the amount of time that pressure was applied for. And this graph shows the relationship between these two variables. So on this axis we have millimetres of mercury, 50, 100, 200, 300, increasing up there. And on this axis we have time. 2 hours, 4 hours, 6 hours, 8 hours, 10 hours, 12, 14, 16. Now what we can do is take any particular amount of pressure and any particular amount of time. Now, relatively high amounts of pressure can be tolerated without pressure sores forming for relatively short periods of time. So for example, if someone is subject to 100 millimetres of pressure, and that is maintained for 2 hours, that will give us a point here on the graph. And under this line here, under that line, a pressure sore will not develop. Of course, this is of course assuming that the person is otherwise healthy. Or a lower pressure, say of 50 millimetres of mercury, for 4 hours, also shouldn't cause any problems. But when you get up to the higher figures, say 300 millimetres of mercury, I think you can see even if the pressure is applied for an hour, then you're probably just over that line actually, and a pressure sore is likely to develop. But anywhere over this outer line, then a pressure sore will develop. So you can see, for example, if a pressure of 200 millimetres of mercury is applied for 4 hours, that will give us a point on the graph there, then a pressure sore will develop. Or taking a lower amount of pressure, 50 millimetres of mercury, over a 10 or 11 hour period, and again a pressure sore will develop. 100 millimetres of mercury over a 6 hour period, again pressure sore will develop then. So the relationship between time and pressure. So pressure sores can be formed by high pressure for relatively short periods of time, or by relatively modest amounts of pressure but for longer periods. Just a few notes then to view what we've said. Short periods of high pressure can be as damaging as long periods of low pressure. Standard hospital type mattresses are not a protection against pressure sores. Shearing forces cause the various layers of the body tissues to move over one another, causing distortion of the capillaries, damaging tissues, and impairment of capillary blood flow. So our main role is preventing pressure and shearing forces. Now some of you might have thought about the feet, that the people standing for a long period of time, and there's a lot of pressure on the soles of the feet. It seems they have a specially designed blood supply to withstand pressure, but given time, pressure sores will form on the feet as well. Of course, when you're standing, very often you're rocking around and relieving the pressure.